Dear Dr. Intan, I'm Jia Mei from BITS S1G2. Our selected topic for a decrease and conquer algorithm is BFS. I'm giving an introduction of BFS and some applications of it. In a decrease by a constant variation, the size of an instance is reduced by the same constant in each iteration of algorithm. Typically, this constant is equal to 1. Figure shows the decrease by 1 and conquer technique. Breadth-first search is discovered by Conrad Juice in 1945. It is one of the simplest algorithms for searching a graph and the architect for many important graph algorithms. It works on both directed and undirected graphs. All adjacent vertices of a vertex are processed before moving to the next level. It begins with traverse through one level of children nodes, then traverse through the level of grandchildren nodes, and so on. Here is the main fact about breadth-first search. The data structure is a queue. Number of vertex orderings is 1. The edge types is mostly tree and cross edges. The main applications is connectivity, acyclicity, and minimum edge paths. The efficiency for adjacency matrix is of modulus V squared. Efficiency for adjacency list is of modulus V plus modulus E. This is the example of breadth search. A is a graph. B is a traversal queue with the numbers indicating the order in which the vertices are visited. In example, added to and removed from the queue. C is the BFS forest with the tree and cross edges shown with solid and dotted line respectively. Applications. In peer-to-peer networks like BitTorrent, BFS is used to find all neighbor nodes. Figure shows each peer forwards the query to all its neighbors. Fault focuser algorithm for computing the maximum flow in a flow network. Next, BFS is also used in the famous Dijkstra algorithm for computing the shortest path in a graph. Figure 6 is an example of a map that BFS can take and return the shortest path. BFS runs on the map and determines what the shortest roads between the cities are and produces the map above, which shows the best paths from city to city. It can also use to test the bipartiteness of graph. A graph is said to be bipartite if all these vertices can be partitioned into two disjoint subsets x and y, so that every edge connects a vertex in x with a vertex in y. One can also say that a graph is bipartite if its vertices can be colored in two colors, so that every edge has its vertices colored in different colors. Such graphs are also called two-colorable. For this example, graph 1 is bipartite, while graph 2 is not. Now, I'm designing a BFS-based algorithm for checking whether a graph is bipartite. First, start with a vertex and give it a color, red. Next, run BFS from this vertex. For each new vertex, color it opposite with its parents. Next, repeat until all the vertices are colored red or blue. Scan all the edges and determine whether there is any edge for which both ends receive the same color. It can also use to detect cycles in a directed graph. Now, I'm going to explain how one can check a graph's acyclicity by using BFS. The function should return true if the given graph contains at least one cycle, else returns false. For example, the graph contains two cycles, 0 to 1 to 2 to 3 and back to 0, and 2 to 4 and back to 2. So this function must return true. The algorithm is first compute in degree, which is the number of incoming edges for each of the vertex present in graph, and initialize the count of visited nodes as 0. Next, pick all the vertices with in degree as 0 and add them into a queue. It is a enqueue operation. Remove a vertex from the queue. It is a dequeue operation. And then Increment count of visited nodes by 1. Decrease in degree by 1 for all its neighboring nodes. After that, if in degree of a neighboring node is reduced to 0, then add it to queue. Repeat step 3 until the queue is empty. So, if count of visited nodes is not equal to the number of nodes in the graph has sky go, otherwise not. Thank you for listening.
Hi, I am Choo Pong from BITS S1G1. Now I want to explain breadth-first search with picture diagram. I will use the queue concept to explain it. So I have a graph here. Let's start our breadth-first search with vertex 1. Firstly, we put vertex 1 enter quit. Then we unquit it and put all the nodes that connect to vertex 1. We put in ascending order, so the sequence is 2, 3, and 4. Then we encrypt first item in queue, which is vertex 2, and put node 5 into queue since it connects to vertex 2. Then we enqueue vertex 3. We put vertex 7 and 8 into queue. We enqueue vertex 4 and put vertex 6 into queue. And lastly, all vertex has been visited, so we just enqueue all items in the queue. Finally, the FS of this graph is 1, 2, 3, 4, 5, 7, 8, 6. That's all for me. Thank you.
Hi, my name is Cecilia from BITS S1G2. The algorithm that chosen by our group is breadth-first search algorithm. It also called BFS. I will present the algorithm of breadth-first search. This is the algorithm of breadth-first search. In the algorithm, there are two parts. The part 1 of the algorithm try to find out all the subgraph. If the graph is destroyed, we will use this part to find out the forest of tree. If the graph is joined, then this would get called only one. At the end of the part 1, it will call a function breadth-first search, which is to create the tree. Then this function is the second part of the algorithm. Let us start to see how the algorithm is worked. First, we will use this diagram to explain the algorithm. We list out all the vertex of the graph and then mark each vertex in V as 0. We also call it as unvisited. After that, we set a variable called count to 0. Then we find any vertex marked as 0. If any vertex marked as 0, we will enter the function breadth-first search. For example, we start with vertex A, it marked as 0, then we will call the breadth-first search function for A. So the function get called and increment the counter by 1. Now the counter become 1. Then we mark the vertex A with counter value. It means that A now become 1. After that, we add vertex A into Q. It also show inside the inside this algorithm. So we mark A with counter initial list query with A, while the query is not empty. So now the query is not empty. So we enter the while loop. After enter the while loop, we will find which vertex is adjacent to A. We first check C is adjacent to A. Then we check that C also marked as 0. Therefore, we will enter the if loop. In the if loop, we will increment the counter by 1 and mark the vertex C with the counter value, which is 2. We also will add the vertex C into the queue. Then we check again which vertex is adjacent to C. If there is any vertex adjacent to the front vertex, it will go through the if loop and add into queue. If there is no any vertex adjacent to front vertex, then we will remove the front vertex from the queue. Until the queue is empty, we will go out from the while loop. Then we will go back here and check any vertex is marked as 0. If there is any vertex marked as 0, we will call again the functions of breadth-first search. Then repeat the step in breadth-first search functions until there is no any vertex is marked as 0. I already finished my part. I will pass the presentation to my teammate. Thank you.
Assalamualaikum. I'm Israt Jahan from BITS S1G1. So today my topic is breadth first search algorithm complexity. So complexity, time complexity. The time complexity of BFS will be O V plus E, where the V is the number of varieties and E is the number of edges. This again depends on the data structure that where we use to represent the graph. And if it is an adjacency matrix, it will be OV to the power 2. If we use an adjacency list, it will be OV plus E. Now, to explain how, let us consider the difference between a sparsely connected graph and a densely connected graph. So, dense graph is a graph in which the number of edges is close to the maximal number of edges. Sparse graph is a graph which the number of edges is close to the minimal number of edges. The sparse graph can be disconnected. Now, what is this mean is that if the graph has so many edges and is still a small graph with only few vertices. So, for example, a graph with 100 vertices but with 450 edges, since it is totally connected, then the number of iteration or resolve call is dominated by the number of edges because 4950 is greater than 100. Now, as n very large, so this difference matters. This kind of graph is a dense graph. The complexity will be OE. Consider another example. So, where the number of vertices is very much larger than the number of edges. This kind of graph is sparsely connected graph, and it may not or be a disconnected graph. Now, consider the graph has 1000 vertices but only 100 edges. Here, some of the vertices are disconnected. So, the BFS in this case will be purely dominated by the number of vertices rather than by the number of edges. So, the time complexity will be OV. So, what does it mean by OV plus E? It means whichever term is bigger will dominate the time complexity. This is why the time complexity of BFS is OV plus E. Now let's move to our last slide, and it is space complexity. So when the number of vertices in the graph is known ahead of time and additional data structure are used to determine which vertices have already been added to the queue, the space complexity can be expressed as where the number of vertices, this is an addition to the space required of the graph itself, which may depending on the graph representation used by an implementation of the algorithm. So, it is more partial to describe the complexity of breadth first search algorithm in different terms to find the nodes that are at distance d from the start node. BFS takes OBD plus 1 time and memory, where B is the branching factor of the graph. Thank you.
Hi, my name is Loh Chun Ren. In this video, I'm going to introduce another algorithm other than breadth first search. This algorithm is called best first search. Best first search is a type of greedy algorithm. It will always select the path which appears best at that moment. This is the combination of depth first search and breadth first search algorithms. The best first search allows us to take the advantage of both algorithms, and with the help of the best first search, at each step we can choose the most promising nodes. This is the step of best first search. Step 1. Place the starting node into an open list. So if the open list is empty, stop and return failure. Step 3. Remove the node in the open list. The node that removed we have the lowest value of hn and place it in the closed list. So once the node n is placed in the closed list, then we have to choose the successor of the node n. Step 5. Check each successor of node n and find whether any node is a goal node or not. If any successor node is goal node, then return success and terminate the search. Else, proceed to step 6. For each successor node, algorithm checks for evaluation function fn and then check if the node has been in either open or closed list. If the node has not been in both lists, then add it to the open list. Step 7 would be return to step 2. This step is repeat until there is no more or the goal node is found. Here we have an example. Consider the below search problem and we will traverse it using greedy best first search. At each iteration, each node is expanded using an evaluation function fn equal to hn, which is given in the below table, which is here. So there is a starting node S and a goal node here, which is the destination. So first, let's start the traverse. In this first example, we are using two lists, which is open and closed list. Following are the iteration for traversing the above example. So as S, the starting node, they will be put into open node automatically, and then it will put into closed list. So then we have to locate the successor for S, which is AB, and it will be put into the open list AB. Then by referring to the table, we have to choose the node with the lowest HN value, so which is B. So B has a more lower value than A, and thus B would be put into close. So iteration 1 will have open list only A, and close will be S and B. So next we will choose the successor of the node that have been put into the closed list, which is B. So the successor of B would be E and F. So these two will be put inside the open list. So iteration 2 would be open E F A and close would be S B. So next we will choose the node with the lowest HN. Let's refer back to the table. We have A, E, F. So F2, E8 and A12. So F is the lowest value of HN. So F will be put into the closed list. So only E and A left here. So next iteration, we will choose the successor for the F. So it will be G and I. So in this case, since G is our goal node, so when the goal node is located in the open list, it will automatically put into the closed list, and then this will end the iteration. We terminate the program. So once the iteration has ended, the final solution part will be decided based on the closed list. So in this case, it will be S, B, F, G. So this is how you do best first search. The advantage of best first search is it can switch between breadth first search and depth first search by gaining the advantage of both the algorithms. This algorithm is more efficient than BFS and DFS algorithm. However, it has its own disadvantage, such as it can behave as an unguided depth first search in the worst case scenario. It can also get stuck in a loop as DFS. And lastly, this algorithm is not optimal. The time complexity for the best first search for the worst case is O, B, M. And the best time complexity of greedy best first search is N log N. The space complexity, there's only worst case, which is the worst case space complexity of greedy best first search is OBM, where M is the maximum depth of the search space. That is all from me. Thank you for watching this video.